Welcome to today's lecture. In the last lecture, we have seen Unit 3, which is completely based on, we can divide our Unit 3 into two. That is, part 1 is entirely based on probability and random process, and the part 2 is entirely based on noise. In the last class, we have seen what is random process, what is random variable, and what are all the random process we have seen in the last lecture. One is stationary random process, and in which we have two classification. One is strict sense stationary, which we in short we refer it as SSS, and the second one is wide sense stationary, in short we refer it as WSS. And after that we have seen ergodic process, in which the time average which is equal to ensemble average. And what is an ensemble average? Ensemble average is taking an average or across the process. When we take an average along the process, then it is referred as time average. When a certain process in which both ensemble average and the time average are equal, then we refer that type of process as an ergodic process. And after that we have seen what are all the characteristics for Gaussian process, and we finally finished that part with white noise. And in white noise, the power spectral density is constant, which means that from the frequency, that means minus infinity to plus infinity, all the frequencies, for all the type of frequencies, our power spectral density is going to be constant. This is one of the very important noise model in communication system. In today's lecture, we are going to see part 2 of Unit 3, which is entirely based on noise. First we will see what are all the type of noise available, then we will see one by one. Mainly we concentrate on internal noise, that is our front end part of the receiver noise. Here in this figure, what is the communication system? What are all the models in communication system? Our transmitter, which generates the which is helping to convert our message signal to it. What are the properties of transmitter? It will boost the power level, and after the modulation, our original information is transmitted to the receiver via a channel. If in case our channel is going to be a wireless, this original information while passing through the channel may get accumulated by noise. And so as a result of it, the receiver is going to receive only the distorted information of the signal. Receiver, if assume we don't have any noise in the channel, then we can completely receive the desired signal as we have sent in the transmitter side. But unfortunately, since we have a noise accumulated over the and this noise may be imposed on the desired signal, therefore our received signal will be in the form of distorted nature. What are all the possibilities, or what are all the reasons for this distortion? Attenuation in the channel, non-linearities in the channel, and one of the most important prime cause for this distortion is our noise. And what is the performance measure of transmitter and receiver, and how we measure the communication system? Based on the three parameters. One is based on the transmission bandwidth, second one is based on the receiver complexity, and the third one is based on the signal to noise ratio. This plays a predominant role in analyzing the effectiveness of our communication system. So our focus is entirely on this. What are all the types of noise which often affects the our channel? We basically divide our noise in terms of external and internal. Before that, if our noise is going to be added to the channel, then we refer that type of noise as an additive noise. If our channel with our desired signal, if the noise is going to be multiplicated, then our type of effect is known as fading. So there are two types of effect. One is going to be additive in nature, and another one is going to be multiplicative, which we refer in terms of communication, we refer it as fading. So it is a prime role to concentrate on what are all the types of noise which may affect our desired signal. So we have to study what are all the types of noise, and we have to analyze what are all the characteristics of the noise, and then we have to design a model to nullify this effect in the receiver. So what are all the types of noise we classified? One is external noise, that is generated external to the source. It means that wire traveling from transmitter to receiver in channel. The second one, the major classification, is internal noise generated within the source, that means in the front end part of the receiver. The main classification in the external noise are three: extraterrestrial noise, and the second classification is atmospheric noise, and the third classification is man-made noise. First we will see what is an atmospheric noise and what are all the possibilities for the atmospheric noise and what may be the reason for atmospheric noise. Can we give some examples? Lightning, thunderstorms, everything are some of the examples for atmospheric noise. What lightning will do? Lightning will be in the nature of electrical disturbances in atmosphere, that is, it create a large volume of current along with the electromagnetic and that abundant random radiation of electromagnetic wave, which may be varying from the band of frequency band of that is electromagnetic spectrum, we know that. So it varying from lower frequency to high frequency band. So therefore this may be in the random manner, everything will be in random in nature. So the field strength of this electromagnetic wave and the electrical pulse will be inversely proportional to our frequency. So what will happen if we have a frequency increase in frequency, this field strength, the effect due to the lightning or thunderstorm will be less. So what will happen, frequencies less than 30 megahertz will be greatly affected by this type of atmospheric noise. Effect will be minimal for very high frequency and ultra high frequency range. Because these frequencies are going to be greater than 30 megahertz, this type of very high frequency and ultra high frequency is having very less effect due to this thunder and lightning. And we'll have a look into extraterrestrial noise. What are all the possibilities for extraterrestrial noise? One is due to the solar noise, which is our own sun, and the second is due to cosmic noise, which is due to the stars. So both are, we know that both are gaseous bodies, heat bodies, gaseous in nature. Sun radiates at 6000 degrees Celsius, so it also contributes the noise, and we know that solar cycle is 11 years once. So every 11 years once this temperature is going to be increased. It peaks for every 100 years. Therefore sun, so our solar system is also contributing the major portion for this noise. And what will happen is, it affects the almost all the megahertz to gigahertz range. But we know that up to 20 megahertz will be filtered by ionosphere. We know that ionosphere is surrounded by the above the earth atmosphere we have ionosphere layer. So below 20 megahertz will be filtered through the ionosphere. So what will happen, above 1.5 megahertz, sorry, above 1.5 gigahertz, in terms of gigahertz, this will be absorbed by hydrogen in the interstellar space. Observed by hydrogen, the presence of hydrogen component in the interstellar space, which is helping us to observe the 1.5 gigahertz range of noise. Interstellar. Therefore, our frequency varying from 20 megahertz to 1.5 gigahertz, this noise range is going to be get affected. So this type of frequency range will be get affected mainly by this solar noise. This is this atmospheric noise is random in nature, and this is also random in nature. Cosmic noise, which is uniformly distributed over the noise, even though stars are present at very large distance from the our earth, but due to the presence of large number of huge number of stars in the system, not only stars, along with other galaxies and suns in the other galaxies, and also our Milky Way, everything will contribute. In each and every system we have a gaseous body, so all this system will contribute a noise. Therefore it will have a range of greater than gigahertz, which is uniformly distributed over the sky. This is this concept is entirely for this cosmic noise. So it varies from few megahertz to few gigahertz. So less than 2 gigahertz, in the sense it will be radiated by ionosphere in presence. But what will happen within the 20 megahertz to 1.5 megahertz, all these frequencies are going to be affected by this cosmic noise. So we have to nullify this effect. And what about this man-made noise? This is mainly in the urban areas compared to the rural, because vehicles, industry, and then automobile ignition, aircraft ignition, and from the smoke from the machines, everything will be predominantly present in the urban areas, and this type of and noise mainly affects the frequency range from 1 megahertz to 500 megahertz. Frequency range. So these are all the three important classifications under the external noise. One is due to the atmosphere, and another one is due to the extraterrestrial noise which is present above the solar system, from the solar system and above the solar system, and another is due to the man-made noise which is present within our urban, most of the noise produced around the urban areas. So the signal transmission in the urban area is predominantly affected by this type of noises compared to our urban areas. And what is the second classification in the noise? The second classification in the noise is internal noise. We have many type of noises present in internal noise, but we are going to see short noise and thermal noise in our syllabus. What are all the types of noise? Partition noise. Partition noise mainly present in BJTs, FETs and pentadiodes and kind of the, semiconductor devices, and low frequency noise, flicker noise, and then high frequency noise, generation recombination noise, short noise and thermal noise. We will see what is short noise and what is thermal noise now. What is short noise? Short noise is produced due to the random diffusion of electrons, and short noise is mainly due to the vacuum tubes, solid state devices or semiconductor devices, photodiodes. What will happen in this type of devices? Due to the random diffusion of electrons at random instance of time, you will have an due to this random diffusion will have a noise. And what will happen in the semiconductor devices or solid state devices? Due to the diffusion of minority carriers or due to the drift of majority carriers or generation or recombination of electron and hole pairs, everything will contribute to the noise. And what will happen in photodiodes? Random diffusion emission of photons will also constitute for the noise in the photodiodes. This is for the short noise explanation. And what for this thermal noise? Due to the random motion, we know that if taken resistor, so this is going some 10K resistor. What will happen if you keep it an idle, but due to the presence of free electrons within this resistor, even if we maintain the 0 Kelvin, if any temperature above 0 Kelvin, this due to the kinetic energy, the free electrons will try to randomly move. So the random behavior of the free electrons inside this resistor will cause the random current flow in the conductor. The random current flow in this conductor will create random voltage fluctuation. So this random voltage fluctuation will create into noise. So this will create a random motion of or movement of electrons. This random motion calls random current flow inside the semiconductor, inside the conductor. This random current flow will create random voltage fluctuations. This random voltage fluctuation will create a noise. This type of noise generated due to thermal agitation is referred as thermal noise. Thermal noise is also referred as Johnson noise. Now we will look into the details of, that is, what are the noise calculations for the short noise as well as the noise calculations for thermal noise. In short noise, we study current generated in electronic devices, that is our solid state tubes or vacuum tubes or semiconductor devices or photodiodes. The current is in the form of discrete pulse. Every time charge carriers moves from, consider a diode, it's an anode, cathode, so it's minus and plus. Always the current will be moving from cathode to anode. Actually, each and everything is in pulse. It's a discrete phenomenon. It appears to be continuous in nature. But actually it's in discrete phenomenon. Therefore, what will happen? The wiggling of current nature will appear. If consider this is our, with respect to t, this is our mean current I, hit up the wiggling of current short noise will appear like this around the mean current, mean value of I. This part is referred as short noise current. This wiggling effect, this fluctuation is referred as short noise. This can be observed in fast acting oscilloscopes. Normal oscilloscopes, I mean in normal CRO cathode ray oscilloscopes, we were not able to identify this fluctuations. Okay, this current appears to be continuous, but it is a discrete phenomenon. Therefore, the fluctuations it appears as random in nature. What is the current equation? I of t is equal to therefore I plus ISN. Therefore, both these at mean value as well as the short noise current contributes to the total current in the vacuum tubes or semi solid state devices. So, this we take it as an equation number 1. This I is referred as the mean value. And what is the mean square value then? Mean square value is expectation of I square of Sn. It is referred as 2QIBN. We take it as equation number 2. This is also referred as Schottky's formula. In terms of the charge as well as the bandwidth. What is Q stands for? Q stands for the electron charge. We know the formula for it, I mean we know the value for it, 1.6 into 10 to the power of minus 19 coulombs. And what is the I? I is the mean value. And what is the BN? BN stands for bandwidth. Bandwidth of the measuring instrument, whichever may be our measuring instrument. So, this is the general formula, and based on this observation, we have observed that this movement is random in nature, the electron diffusion is random in nature. Therefore, a short noise can be characterized as an Gaussian process. Important property of short noise is it is characterized as Gaussian process. How and why? Mean value is equal to 0. How it becomes 0? The number of electrons contributing to the diffusion is very large. Number of electrons contributing to the diffusion, random diffusion, right? So, that this will be very large. Therefore, our mean value will be 0. And the second property in Gaussian processes, variance value is equal to 1. How it becomes 1? Random emission from each and every random emission from the cathode is statistically independent. So, since it is statistically independent, our variance value is 1. We know that by central limit theorem, if we have a mean is equal to 0 and variance is equal to 1, according to central limit theorem, CLT in short, it stands for central limit theorem. So, according to our central limit theorem, if we have a mean is equal to 0 and variance is equal to 1, then this type of process can be indicated as an Gaussian. Following Gaussian distribution. So, a Schottky noise model is in Gaussian following the Gaussian process. This equation 1 and 2 stands for the vacuum tubes. If in case our instrument is going to be solid state device, our mean current value will be I is equal to Is e power QV by KT minus Is. So, everything is going to be some formula. This will be mainly useful for our problem calculations. Therefore, we know that Is is the saturation current, Q stands for the charge, V stands for the voltage, K stands for the Boltzmann constants, based on the quantum mechanics, right? T stands for absolute temperature, 0 Kelvin. Therefore, the mean square value, what will be the mean square value then? Mean square value is given by expectation of I square Sn, same as in vacuum diodes. Therefore, 2q I plus twice the Is into Bn. So, this is the yet another formula for short noise. Now, we are going to see what is the noise calculations for thermal noise. We have studied thermal noise is generated due to the random movement of electrons. This is due to random emission or random diffusion. Generation and combination. Of mainly due to the electrons and also due to electrons and holes combination. Generated due to here random movement of electrons. Okay, this type of noise will appear like this. When we observe a multimeter across the resistor, we can easily identify this type of noise. Due to this free electrons, the movement of free electron due to Brownian movement, we can observe this voltage fluctuations across the conductor. Thermal noise is zero in perfect conductor. Actually, it is thermal noise. There will be absence of thermal noise in perfect conductors. And what is the mean square value? Mean square value, everything we have calculated in terms of current. In thermal noise, we calculate in terms of voltage. So, the expectation of Vn square of T is equal to ensemble value. Therefore, Vn square of T whole bar is equal to 4 K T R B whole square. What is K? We know that K is in Boltzmann constant, T is the absolute temperature, R is the resistance and B is the bandwidth. Therefore, thermal noise is, since we have taken it as an ensemble average, the thermal noise is it is a stationary process. That is, we have not applied any electric field into it. Therefore, it is before applying the electric field, we are observing what is the voltage across this resistance. Therefore, it is a stationary process, as well as the time average is equal to ensemble average. Mu x is equal to this time average. What we refer when our time average is equal to ensemble average, we refer this as when time average is equal to ensemble average, we refer this as an ergodic process. So, when we have, assume we have several resistors. This is 1, 2 and we have another one called 3. So, when we measure across as well as along, this is referred as time average. If you measure across, it is measured as ensemble average. So, when both of these are equal, then we refer that type of model as an ergodic process. In terms of current, the same mean square value in terms of current, expectation of I square of n of t is equal to I in terms of ensemble value is equal to 4 K T. R can be replaced by G, therefore, 1 by R, therefore 4 kT GB amp square. The noisy resistor R model can be drawn with the help of Thevenin and Norton equivalent. So this is R, this is the voltage equivalent, V mean square value plus and minus. So this is for the noiseless resistor. This is our Thevenin equivalent. Same for Norton equivalent in terms of the voltage source is replaced by current source. IN square of T. This is G. G is equal to 1 by R. This gives our Norton's equivalent. This thermal noise is again our thermal noise is Gaussian distributed. It means just now we have seen mean is equal to 0 and variance equal to 1, then we refer the type of model as an Gaussian distributed. Mean is equal to 0 due to number of electrons generated is very large and variance is equal to 1 due to statistically independent nature, random motion of electrons. Therefore, by central limit theorem, n is equal to 0, 1. Therefore, we refer this thermal noise as a Gaussian process. From power transfer theorem, the power transfer will be maximum when the load RL is matched with the source R. Therefore, Vrms is equal to for deriving the maximum average noise power, we will first find out what is the RMS value. Therefore, RMS value is V square N of T divided by 2. So, this is a RMS value using the Thevenin's equivalent. Therefore, maximum average noise power or available noise power, both are same. Available noise power or maximum average noise power. We refer in terms of PA, which is equal to V square RMS divided by R. We know that from the Thevenin's equivalent, when will be, if we assume we have an load across this, which is equal to ZL. Therefore, ZL, if this is a source, then ZL is equal to ZS, the power transfer will be maximum. Therefore, according to the power transfer theorem. Therefore, Vrms is equal, to calculate the maximum average noise power or available noise power, our formula is V square RMS divided by R. V square RMS is V square N of T divided by 4R. This is ensemble value from here. Therefore, we know that V square N of T, that is mean square value of the thermal noise is 4 kT RB divided by 4R. Therefore, our PA value is equal to kTB watts, unit of power. You see, from here it is observed that our available noise power is independent of the R term, that is resistance term. By using the Norton's equivalent, we similarly from the voltage equation as well as from the current equation, we can easily identify this available noise power is equal to kTB. This is if in case of ZL, ZS, RL, RS. And we can note down some of the properties for thermal noise. This will be extremely helpful for our problem solving. What is the variance formula? Variance is sigma square V is equal to 2 pi kT whole square divided by 3h R whole square, where K is the Boltzmann constant, H is the Planck's constant, and the second one is mean square value. Just now we have calculated the mean square value for current as well as the voltage. Vn square of T is equal to 4 kT RB whole square. In square of T in simple 4 kT GB amp square, and power spectral density PSD in short, ST for thermal noise is equal to 2 kTR watts per hertz Since this is a constant, power spectral density is constant, it behaves like an white noise process. Available noise power PA is equal to KTB watts, and the fifth one is available noise power spectral density. Available noise power spectral density is N of F is equal to 1 by 2 into KT hertz. If all the resistors connected are in series, then we can resist, right, if R1 plus R2, if it's connected in parallel, then the equivalent resistance RE will be is equal to R1 R2 divided by R1 plus R2. Therefore, our final value will be Vn square of T is equal to 4 KT R, this is RE into B, depending upon the if our resistance is in series combination or in parallel combination. So, from this observation we identified this due to the power spectral density constant nature, autocorrelation function will also be constant. Therefore, that is, if this is constant in nature, autocorrelation, see, just now we observed that white noise process, which is N0 by 2, if this is constant in nature, the Fourier transform of it will give impulse function. Therefore, the autocorrelation function of ACF, in short, autocorrelation function of thermal noise process, will also be in the nature of impulse. We will see here comparing to with respect to white noise. See, we know that white noise is W of F is equal to, power spectral density for white noise is equal to N0 by 2 watts by hertz. Therefore, all frequency components in white noise will contribute equally to the noise power. Therefore, PA is equal to N0 into B watts. This is equation number 1. Our noise term is equal to KT into B for thermal noise, KT into B. This is equation number 2. So, by equating both 1 and 2, N0 is equal to K into T. Therefore, SW of F is equal to, can be rewritten as KT divided by 2. Noisiness of the noise source is represented in terms of equivalent noise temperature. Therefore, TE can be replaced by, we know that PA is equal to KTB from this equation. So, therefore, TE can be replaced by TE, effective equivalent noise temperature. Therefore, T in term, we know that N0 is equal to KT. Therefore, N0 can also be replaced by K into TE. Therefore, TE is equal to N0 by K. What is the Fourier transform of power spectral density? Power spectral density term is 2 KTR, or power spectral with respect to white noise, KT divided by 2. Therefore, power spectral density or autocorrelation function is given by RW of tau is equal to N0 by 2 dou of tau, that is impulse function when tau is equal to 0. For rest of the terms, when tau not is equal to 0, this value will be 0. This we have calculated as N0 by 2. Therefore, the power spectral density will be similar to that of an impulse function. Therefore, autocorrelation function of white noise and autocorrelation function of thermal noise will be impulse in nature. Therefore, white noise processes, we refer this white noise process is also as Gaussian process. Any two samples are uncorrelated in nature. Theoretically, white noise is having infinite average power, but power spectral density is constant up to, power spectral density we observed here is constant up to 10 to the power of, in practical communication system, is constant up to 10 to the power of 13 hertz practically. All our communication system will be covered with in this range.